Okay, good afternoon. In the last session, we have discussed about Clapeyron's theorem of three moments for the analysis of continuous beams. On that, we will be solving some numerical examples with constant flexural rigidity. Continuous beams with constant EI value. Different conditions we will see one by one. Now let us see the continuous beam with flexural rigidity being constant for all the spans. Yeah, it reads like this: a continuous beam ABC 10 meters long rests on three supports A, B and C at the same level and is loaded as shown in the figure. Determine the moments, support moments, and draw the bending moment diagram. Up to that, we will see calculating reactions and drawing shear force diagram. That we will see later. Now, the beam is simply supported over three spans, over three supports A, B and C. Span AB being 6 meters and BC being 4 meters. And loaded with a point load on AB and UDL on BC. Okay. Now, the general bending moment diagram for this will be something like this. Okay. Yeah. It will be something like this. Okay. Yes. This is obtained by overlapping or superimposing simply supported bending moment to fixed bending moment. Okay. Overlapping simply supported or free bending moment diagram over AB, which is a triangle. Okay. And overlapping that or superimposing that over the bending moment diagram due to end moments. And the condition here is bending moment at A and bending moment at C are 0 being simply supported. So the only unknown we have in this case is moment at B, MB. Okay. So in case of simply supported beams, the only unknown is moment at the intermediate support. Okay. And that will be directly obtained by applying theorem of three moments for spans AB and BC. Okay. Yeah. Here what is given is span L1 is given 6 meters, span L2 is given 4 meters. Okay. And for drawing simply supported bending moment, this moment will be WAB by L. W is given 3 kilonewtons, A is 2 and B is 4 meters, and here L1. And here the maximum bending moment is at mid-span, positive bending moment, maximum positive bending moment at mid-span. Okay, and it is equal to WL square by 8. So W is here UDL 1 kilonewton per meter, L is 4. So WL square by 8 is the maximum bending moment at here, mid-span of BC. Okay. Now finding this moment MB for the intermediate support, we can draw the bending moment diagram. Okay. Yeah. Okay, and with this data, first we will draw the simply supported bending moment diagrams. Simply supported bending moment diagrams over spans AB and BC. Okay, so the bending moment at the point of application of load, that is point B, is WAB by L1. Okay, WAB by L1. This is the point B, and we will take point E at midspan, where the bending moment is maximum. Okay, so at midspan of BC, at point E, it is WL2 square by 8. So you will be getting it 2 kilonewtons. Here it is 4 kilonewton meter. Okay. So the simply supported bending moment diagram will be something like this. Okay. So this is 2. Now, area of this diagram A1 and area of this diagram is 8. So we'll find out these areas also. Area multiplied by centroidal distance, actually. Area multiplied by centroidal distance from A. And for this, centroidal distance is measured from B. Okay. This is x2 bar and this is x1 bar. In this particular case, we directly do not know the centroid of this triangle. So we split this into triangles AD, we call it ADF and DBF. Okay, two triangles. Two parts will split this, and for each part we will find the moment. So for this, base is 2 and height is 4, and area is half base into height. Centroidal distance is 1/3 of 2/3 of 2. From A, it is 2/3 of 2. Okay. Yeah. So we will get this is 16 by 3. Okay. And for the second part, area is half into base 4, height 4, and centroidal distance is 2 plus 1/3 of 4. 2 plus, this is 1/3 of 4. Okay. So we will get this moment of part 2. So A1 x1 bar equal to this plus this. Okay. Yeah, that's what we are going to see here. A1 x1 bar is moment of, this is area, and centroidal distance is 2/3 of 2. Similarly, this is area of second part, and centroidal distance 2 plus 4 by 3. So we are getting this 32. And coming to span BC, A2 x2 bar. So area is for a parabola 2/3 of BH, 2/3 of base into height. Okay, 2/3 of base into height. So what is the base here? 2/3 of base. Base means 4 meters. Base is 4, span, height is 2. So this is area into centroidal distance from B. C. From C. So it is 32 by 3. Okay. Now you apply the Clapeyron's theorem of 3 moments for spans AB and BC. With constant EI, the equation is in this form: MA L1 plus 2MB L1 plus L2 MC L2 equal to minus 6 A1 x1 bar by L1 plus A2 x2 bar by L2. 680 x to the power. So here MA is 0, we know that. MC is also 0. So we have 2MB into L1 plus L2, 6 plus 4. And on the right hand side, 6 by L1, that is 6 into A1 x1 bar, that is 2. Second is 6 into A2 x2 bar, 32 by 3 by L2, 4. Okay? Yeah. This is with negative sign actually. Minus. Okay? So, minus 48. MB will be minus 2.4. MB will be minus 2.4. And the reactions are calculated by considering free body diagrams of spans AB and BC separately. Okay, after that, shear force diagram will be drawn. And for the given beam, now the bending moment diagram will be of this shape. This is 4, this is 2.4. Okay. Yeah, 2.4. And free bending moment diagram. So, the net bending moment diagram will be, it is shown in this hatched lines. This is the net bending moment diagram. Okay. It can also be drawn something like this. 2.4. Okay. 2.4. Superimposing, you will get something like this. And for this, you will get something like this. Yeah, either this one or this one, both are correct for this. And these points are called points of contraflexion. Points of contraflexion. We can locate them by equating bending moment to 0. Yeah, this is the bending moment diagram. Okay, just now I have said. Okay, this is obtained by superimposing positive bending moment and negative bending moment diagrams. Now let us see another example. A continuous beam ABCD. This beam is of 3 spans. Okay, 4 supports we have. Simply supported at A, B, C, and D is loaded as shown in the figure. Find the moments over the beam and draw the bending moment and shear force diagrams. Okay, so just you look at the loading diagram. We have 4 supports A, B, C, D, and what is known here initially is moments at A and D are 0. So the unknown moments are at intermediate supports M, B, and MC. 2 unknowns we have, and you will get 2 equations in MB and MC by applying theorem of 3 moments. Once for spans AB and BC, and next for spans BC and CD. Okay, because we can apply this for 2 spans at a time. 2 spans at a time. Is it? So first you find out the bending moments at points E, F, and midpoint of CD, midspan of CD. That means you can call it as say G. Bending moments at E, F, and G you find. What is the bending moment at E, for example? W1 A1 B1 by L1. What is L1? 6. L2 5. L3 4. A1 is 2 and B1 is 4. A2 is 2 and B2 is 3 because it is 5. 2 minus 2 plus 3 5. Okay. So MD is MF bending moment at this point is W2 means 8. W1 is 9. A2 B2 by L2. And bending moment at G is W into small w here, UDL, L3 square by 8. WL3 square by 8. So first we will calculate this bending moment diagram to draw the simply supported bending moment diagram. So spans AB, BC and C. Okay. This is the data given. And now ME W1 A1 that is 12, MF W2 A2 B2 by L2, and bending moment at midspan of CD that is at point G WL3 square by 8, 6. Now we will draw the free bending moment diagrams as shown. How are they? That is 12, okay, 12, it is 9.6, next 6, bending moment at G, this is F, this is E, this is G, it is 6, A, B, C, D, okay. Now we split this into two parts, this also into two parts, because we directly don't know the centroidal distance, we split it. Now apply the theorem for spans AB and BC. For that we will find out A1 x1 bar. What is x1 bar here? Distance of centroid of area A1 from support A, that is important, from support A. And A2 x2 bar is distance of centroid of A2, this is area A2, and this distance is from support C. This distance is from support C. This is when we apply the three moments equation for spans AB and BC. So distances x1 bar and x2 bar are measured from A and C respectively. Similarly, when you apply this for spans BC and CD, second time, when you apply this theorem for spans BC and CD, then A2 x2 bar and we will find A3 x3 bar. This time x2 bar is measured from B, not from C as measured here. Because we are applying theorem for spans BC and CD, the distances are measured from B and D. So x2 bar is this time from BC, from end B, and x3 bar is from D. X3 bar is from D. Is this clear? You have to note this point. While solving the problems with more than two spans, you have to be careful here while calculating moments of area. Okay. So the calculations are shown here. A1 x1 bar. First part half into base is 2, height is 12, and 2/3 of 2. Okay. And for the second part of triangle. Half into base is 4. We have seen this here. Base is 4, this is 4, and this is 2. For this part, half into 4 into 12, that is area. And distance centroid from A is 2 plus 4 by 3. 2 plus 4 by 3. So this is 96. A2 x2 bar. So this is measured from C. Distances are measured from C. Here also, for first part, for this part, area is half into 2 into 9.6, and centroidal distance is from C. What is it? 3 plus 2 by 3. 3 plus 2 by 3. And for this part, the centroidal distance of 2/3 of 3. 2/3 of 3. So here, half into 3 into 9.6 and 2/3 of 3. And for this part, it is 3 plus 2 by 3. And this meant you are getting 64. Next, for spans BC and CD. BC and CD. So, the moments are calculated by taking distances from B and D respectively. Okay. For BC, distance is measured from B. For CD, distance is measured from D. Okay. Yeah. Same, similar. Okay. You're getting this 56 this time. A2 x2 bar. This A2 x2 bar and this A2 x2 bar are different. They are not the same. Because here the distance is from C. Here the distance is from B. X2 bar is from B. Okay. And A3 x3 bar distance is from D. Here you can directly calculate for entire area because we know the centroidal distance is 2 because of symmetry. Okay. Yeah. Now apply this theorem. Substitute the values, calculated values here. This is the equation for spans BC and AB and BC. MA plus 2MB into L1 plus L2 plus MC L2 equal to minus of this. MA is 0, we know. So 2 into MB into 6 plus 5 plus MC into 5 equal to these values. After substitution, we will get the value as 172.8 minus. So this is first equation in MB and MC. First equation in MB and MC. Now apply the theorem for BC and CD. Apply this for BC and CD. So MB L2 plus 2MC L2 plus L3 and MD L3 equal to this 6A3 x2 bar by L2 plus 6A3 x3 bar by L3 minus of that. So here MD is 0, so last term becomes 0. So you will have 5MB plus 18MC equal to minus 115.2. And this is the second equation in MB and MC. So by solving these two, we will get MB and MC. Minus 6.84, minus 4.48. Okay. So bending moment diagram we can draw now. Bending moment diagram will be for span AB, BC and CD. So here 9.6, here 12. Okay, this is free bending moment diagram or simply supported bending moment diagram. This is 9.6, and here parabola with maximum ordinate 6. And bending moment at B is 6.64 minus 6.64, 6.847, and this is 4.48 minus 4.48. So MA is 0, bending moment at A is 0, this is 6.84, and this is 4.48. So join these two and join this with C. So here net bending moment diagram, the hatched portion. This will be the net bending moment diagram. Okay. The same is drawn like this also. Okay. Something like this. This is 4.48, 6.84, and here this one. Both are correct. Both are correct. Okay. Now we can find the reactions. So reactions are obtained by considering free body diagrams of each span. Okay. Free body diagram of AB. So this is 12 load. Is it 12? The loading 9 and 8 kilometers. Okay. This is 9, and bending moment at A is 0. Bending moment at B is 6.84. So the reactions are RA, and this is RB1. Next, for span BC, this is 6.84, and at C we have the moment of 4.48, and the load at AF, this is E, 8 kilonewtons. Okay. This is RB2, and this reaction is RC1. Next, for span CD, we have UDL, bending moment at D is 0, bending moment at C is 4.48, and loading is something here. What is it? Okay. Now, this is RC2 and this is RD. Okay. So, this is now a simply supported beam with load 9 kilonewtons and moment couple acting at B. So you can find the reactions just by applying equilibrium conditions RA and RB1. Similarly, for this span, we'll get RB2 and RC1. The total reaction RB is sum of RB1 and RB2. Similarly, the total reaction at RC is sum of RC1 and RC2. Okay? Yeah, we'll get the total reactions at RB and RC, intermediate support, by summing up these two. Now, once you know the reactions, it is known how to draw the shear force diagram. Okay? Yeah. This is the bending moment diagram as we have already drawn, and this is shear force diagram. Okay? This flat path in shear force diagram shows that the shear force is constant between E and B means there is no load between E and B. Similarly, there is no load between A and E. We have a point load at E and no other load at in AB, in portion AE and EB also. Okay. Similarly, BF, there is no load in between. Similarly, F and C, there is no load in between. And this straight line variation of shear force shows that there is a uniform variation of load. That means uniformly distributed. It indicates uniformly distributed load over the span. Okay. That's all for today's session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.